Okay, now we will go quickly over the basic properties of logarithms. Okay, the first property is that if you have log a of x times y, this splits into two logs. As log a of x plus log a of y. So you should picture this as like literally splitting two logs. I mean, splitting one log into two logs. So you take an x and you just chop it off right here, and it becomes two logs. I'm saying this because often people mistake this rule for saying, oh, multiplication is the same as addition, then forget that there's another log here. What's more important is that one log becomes two logs. Okay, usually I don't talk about proofs that much, but I still want to show you the proof of this, although you don't have to understand it fully. Because if you see the proof, it shows you that this rule actually just comes from the exponential rules that you already know. So proof, say you have log a of x times y. Okay, I want to use the cancellation law backwards. So instead of trying to simplify, I'm going to make it harder. So I'm going to say x is really a to the log of a of x, and also y is a to the log of a of y. So it looks like instead of making things easier, I'm making things really hard. But it's not that bad. Just remember that when you cancel the log a of x with this log a with a, what remains is just x. Here also just cancel a with log a, what remains is y. So if you cancel them, you come back to the previous one, which is log a of x times y. Now, think about what happens if you multiply two exponential expressions with the same base. They have the same base, a, right? So you should be adding the exponents together. So you have log a of log a of x plus log a of y. So this entire thing is together. And then now you can use the cancellation law to cancel these two, and finally it's going to lead you to log a of x. This is what's left, right? So log a of x plus log a of y. So that's it. Just 1, 2, 3 equations, and you're done. You can easily see why these two are equal. The reason is at the center, the rule that's giving you the logarithmic rule is the exponential rule, where you multiply the exponents add up. Now let me show you an example. Without an example, it's going to be hard to figure out what it means. Okay? So example, suppose you have log of 2 radical 2. Actually, this is something that I did solve in the previous video. So if you were taking notes or something, you can look at the answer and compare them. It'll be the same. This is a product of 2 and square root of 2, right? So I can apply the above rule to say this is log 2 of 2 plus log 2 of square root of 2. Then I should think about these numbers as powers of 2. So 2 is 2 to the first power, whereas square root of 2 is 2 to the 1/2 power. Therefore, when you cancel the log 2 with 2, just like this, you end up with 1 plus 1/2, which is 3 over 2. And this is exactly the answer that we obtained in the previous video, so you can again be sure that this rule does work. Okay, there's a second rule that's very similar. It just means log of a x divided by y. If you have division, you, instead of adding, you subtract. And I don't want to show you the proof of this. It's proved in exactly the same way as the formula 1. Okay, just turn this x into a to the log a of x and y to the a to the log a of y, and then use the exponential rule to say division means subtracting the exponents, and you end up with this. Okay, so that's something that you can do to try to convince yourself this is really true. Okay, now the third rule says that if you have some exponent inside the log, that exponent can jump out of the log like a frog. So I like to call this frog over the log rule, although that's not the standard name for this, but I like it because it gives you this image, frog over the log rule. Okay, frog over the log rule. Okay, the rule is that exponents inside the logarithms, they jump outside like frogs. That's the rule. Okay, so that's what logarithms rule. These three, 1, 2, 3, are the most important logarithmic rules. Let me give you an example of this one. So as an example, suppose you were to do log 3 of square root of 3 over 3 squared to the 5th power. Okay. Now there are two ways to compute this. One by just using the exponential rules, and another just using the log rules that we've done. Okay. In the beginning, let's write down square root of 3 as 3 to the 1/2. Okay, now let me show you two different ways. Solution 1, using the exponential rules and only applying the log at the end. So the above is same as the following. It's since you're dividing with the same base, you're subtracting. So 3 to the 1/2 power and 3 to the 2nd power, these are divided, so you have to subtract the exponents. And that is 3 to the negative 3 over 2 to the 5th power. And then the exponential rule says when you have two exponents, they multiply. So you have log 3 of 3 to the negative 5 times 3 is 15, so 15 over 2. And finally, they cancel to give you the answer negative 15 over 2. Okay, now let's see how you can do this with logarithmic rules. In logarithmic rules, 5 can jump over the log. So you have 5 times log 3 of 3 to the 1/2 power over 3 squared. Okay, there's one thing that's slightly dangerous when I just say casually it's the frog over the log rule. The frog can jump over the log if it's the only exponent inside the log. Just like if it's like exponent shading the entire thing of the log. Okay, so this exponent can jump over the log only if it's exponentiating everything that's inside the log. Just like this. So this 5 can hop over, whereas these 1/2 and 2, those are not allowed to hop over. Instead, you have to use the fact that you're dividing, so you have to use this number 2, which says 5 times, you have to subtract log 3 of 1/2 minus log 3 of 3 squared. And now since these cancel, you end up with 5 times 1/2 minus 2, and, oh sorry, it should be parenthesis, and 1/2 minus 2 is negative 3 over 2, times 5 does give you negative 15 over 2, exactly like the other one. So these three are very important. We will probably do other examples with this. Okay, let me list what we have so far. We have the two rules where you can chop off a single log into two parts. So when you have division, it chops off into two logs. It breaks into two logs, and they add up. And number 2, log a x over y, that breaks up again into two logs, this time with the minus. And then number 3, the frog over the log rule, which says c, if the exponent is exponentiating the entire thing of the log, then they can jump over the log, and it becomes like log a of x. C log a of x. Now let me talk about the fourth one. And by the way, I didn't show you the proof of neither 2 or 3. They can be done in a similar fashion as we have done in number 1, and they all have corresponding exponential rules. There are exponential rules that make these work. So that's again some good exercise to do. Now let me talk about something called the change of base formula. This is a standard name, not something that I made up. Change of base formula. It does this. Log a of b is same as log c of b over log c of a. That's what change of basis formula is. The change of base formula is important when you try to use the calculator, especially some scientific calculator, to calculate logarithms for any numbers. So for example, if you have any kind of a scientific calculator with some bunch of buttons here. Now if you wanted to find out log 2 of a using your calculator, nowhere you would see log with base 2. Instead, there will be two kind of functions provided by your scientific calculator. One is log with nothing under it. That's called the common log, and that really means log with base 10. So the common log is log with base 10. If it's 10, people just omit it. So this is called a common log. And there's another kind of log. It doesn't look like a log, but instead it's written as ln of x. That really is a log with base e, where this e is some mysterious number called the natural number, 2.71a, 2a, 1a, and so on and so on. And this is called a natural number, but to show why it's natural, it takes a long time to explain why it's natural. So maybe at some point in calculus you'll be able to understand why this is natural. But at this point you just have to accept that this is something called a natural number. Its approximate value is 7.2183 or something. Okay, so these are the only kind of logarithmic functions given to you. So how are you going to calculate log 2 of 8? Well, the base change formula is what saves us in this case, because log 2 of 8, according to the base change formula with c being 10, this is log 10 of 8 over log 10 of 2. So in your calculator you can just write down log 8 divided by log 2, and just dividing those two numbers, you will see that you're going to get the number 3. So that's the reason for the change of base formula. It's very useful when you find the logarithmic values using your calculator. Now, let me show another example of the change of base formula, because it's not the only time that's useful. Say you wanted to do log 4 of 8. Well, 8 is neither 4 to the first power or 4 squared. I mean, if you think carefully, it's really 4 times square root of 4, but that's a little hard to think. So rather than taking that approach, you immediately think about number 2, because 4 is 2 squared and 8 is 2 cubed. So you can invoke c as equal to 2 and use the base change formula. See, in this base change formula, log a of b equals to log c of b over log c of a. This c can be arbitrary. It has nothing to do with a or b. You can just put this as 10 or e or 2 or whatever, okay? And you just choose the c value so that's convenient for you. And I chose 2 because, by the way, this is 4, 8 and 4, 8 and 4. I chose 2 because both 8 and 4 are exponents of 2. And therefore, once you write it in that form, 8 is 2 to the third power and 4 is 2 squared. So these two cancel, and you end up with 3 over 2, and that's the answer. Okay, now you may have wondered what would happen if you do log 2 of some number that's nothing related to 2. So, for example, how would you do log 2 of 3? That cannot be done by hand, because 3 is not 2 squared, it's less than 2 squared, it's bigger than 2. It's not like square root of 2 multiplied to 2. It's just a number that's totally unrelated to 2. So to calculate log 2 of 3, you can't use the previous methods that we are using. So instead, the only way you can calculate this is just through a calculator using the base change formula. And my calculator says that this value is about 1.58496. Okay, it's about that. Okay, and it doesn't come out as a rational number. It cannot be a fraction. It's some irrational number. All right. Now, why does the base change rule work? Let's try to find a proof for the base change formula. And this is not very easy, so it may be hard for you to understand, but looking at proofs can deepen your understanding of how things work. So let's see. Suppose you have log base of a of b. Now the way you do this is you first multiply log base of c of a. Okay, so where does this come from? So that's why the proof is a little bit hard. So let's just compute the product of these two and see if we can simplify them. Now I can change the order and write this as log a of b times log c of a. That's because multiplication is commutative. I can change it. And then, for a moment, just forget this was something complicated. After all, you can use a calculator to evaluate its value. So this is a number. A number in front of the log, what can you do with it? Well, just like exponents inside the log can jump out, this can also jump in and become the exponent of the thing inside. So this log a of b jumped over the log like a frog and became the exponent. And now suddenly you see that this is something that can be simplified by canceling the a and log a, and you get log c of b. Okay, so we established that log c of a times log a of b is equal to log c of b. And that's almost the proof, because if we divide both sides by log c of a, then these two cancel and you get exactly the base of change formula. Okay, so that's the proof. Okay, now let me finally explain what logarithmic function is. Until now, I only explained the logarithmic function as something that cancels with the exponential function, and we've been using it, and that was good enough definition for us to play with it. But suppose, let me title this as logarithmic functions as inverse function of the exponential function. Okay, so think about the following. Suppose you're given this function f of x, and that's an exponential function over some number a. So a is something positive, and a is not equal to 1, and f of x is a to some power of x. Let's say that's a given function. And let's say we have a question here we need to solve. Find the inverse function of a to the x. How do you do this? Okay, so let's try this. Solution. How do you find the inverse function? First, fx is the output. We are going to call the output as y and input as x. And inverse function, this -1 does not mean it's a reciprocal. It means it changes the input and output. So to get the inverse function of a given function, you have to switch x and y. So if you switch x and y, if x and y are switched, which means that instead of y you put x, instead of x you put y, this is what you get. And then, since I want to know what kind of output y you get when you plug in for x, you want to solve this equation for y. Okay? How do you solve for y? Well, we use the cancellation law. We can take the log a of both sides. See, I have these two sides equal, and I'm treating both sides equally. I'm treating them with log of a, so they should still be equal. Now when you do this, you see something that can be cancelled, right? When you cancel these two, you end up with y equal to log a of x, and that's your inverse function. What did we find out? We found out that the inverse function of this given exponential function is indeed log with base a of x. Okay, so the simple way to define a log, if somebody asks you, what's a logarithmic function? Well, you can just say, oh, it's the inverse function of a to the x function. or the exponential function. It's the inverse function of the exponential function. However, when it comes down to actually calculating what logarithms are, calculating some given expressions in terms of logarithms, it's much better to think of logs as cancellation laws, because if you can cancel, then you can practically figure out all kinds of logs. Now I want to conclude this video with one last important thing. What is log a of 1? Okay, there are 3 different ways to get this. Okay, let me show you all 3. First is you can write down log a of 1 equal to log a of 1 divided by 1, right? 1 is same as 1 divided by 1, right? And then 1 divided by 1 is log a of 1 minus log a of 1, because division splits into 2 logs. The log splitting rule gives you 2 logs. And what are you getting? You're getting the same thing subtracted to itself, so you're going to get 0. Anything subtracted to itself is 0. I like this proof. It's pretty cool, because initially you start with no knowledge of log a of 1. You still don't know what log a of 1 is. You still don't know what log a of 1 is, but then you know that if it's some value, it's going to subtract to itself, so the only way it can be is 0. So it's kind of nice proof. Another way to approach this is to think about log a of 1 as the following. 1 is equal to 1 to the 0th power, isn't it? If you take anything to the 0th power is 1. So log a of 1 is log a of 1 to the 0th power. But then this exponent hops over the log like a frog, right? So it's 0 times log a of 1. And even if I don't know what log a of 1 is, it's some value times 0. What can it be? It's 0. Yeah. So that's another fun way to do it. Well, the correct, or the most widely used explanation of log a of 1 equal to 0 is the following. It's simply that 1 is a to 0th power, and they cancel, and that gives you 0. So that's just sticking to the definition, but that's not as fun as the other two. Okay, that's all for this video.